Welcome back to ECE 501B. As an announcement, your passport is due, I believe the 31st is on a Sunday, so don't let that spoil your 3-day weekend, but that just gives you a timeline to possibly turn in your passport. Homework number 1, I need to create, but hopefully it will be out there at some point, and that's due a week from Friday, is the plan. Today what I want to do is a fairly good list, but we will start by simply returning to what we talked about last time, which was vector spaces, recap that so that you remember what we're talking about, and maybe we'll give more examples than what we had last time, and some that maybe aren't as intuitive or as immediately sort of imagined in terms of what could constitute a vector space. We will simply state some of the properties that are associated with vector spaces, and those are supposed to be consistent with what you have in the textbook as propositions 1.2 through 1.6. We're obviously in chapter 1. Then we will talk about the different proof techniques that you could use if you start proving things in this class, and that is summarized in the inside cover of Solo, that other book that was an optional textbook for this class. Then we will go ahead and go through and prove one of those propositions, and in particular proposition 1.3, and we'll use the proof technique contradiction by contradiction to do that proof. Then we will start to define and discuss subspaces, and subspaces are not the same as subsets. We could have a set of objects, and we could have a subset of that set, but that subset is not necessarily the same thing as a subspace. And we'll go through ways of verifying that a subset of a set is indeed a subspace. If we have time, which I'm not sure we will talk about vector space sums, which is different from unions of sets. So you have to kind of keep track of what we're talking about when we talk about a subset and a subspace. Those are not the same. We will talk about combining vector spaces by a sum operator, and then we will talk about vector space direct sums. That may not be today. It actually may be Labor Day, and you'll get to watch that via a video recording. Maybe we'll sort of do that offline, is what I'm thinking, so that we can squeeze that material in, which is still a part of Chapter 1. Did anyone here in the live class actually watch any of the video? Some of you did. Was it okay? I did that in the convenience of my own office, but hopefully this one will work this time today, and I won't have to repeat the lecture. I was curious if it was viewable, and I'm assuming from your response that maybe it was. Here's a recap of what we talked about last time, and that's this notion of vector spaces. This gives you maybe more of a pictorial representation of that, but we now have a set. So remember, we had 3 different things that needed to come together properly in order to define a subspace. One of those things was a set of objects. Those were our vectors, and now we needed to associate with those 2 binary operations. One of those binary operations takes 2 pieces from the set and combines those vectors via addition, and that may be conveniently denoted as this plus sign. The other operation is scalar multiplication, and there the scalar is an object from our field that we've agreed to be using in this vector space context. And generally in this class, that field of scalars will be our real number line, or the set of complex numbers. The set of real numbers or the set of complex numbers. As a way to maybe get you to watch the video, I did talk a little bit more specifically in the video about fields, as far as the properties of fields, which I didn't necessarily go through in the lecture portion of last Monday. But that's now available, and you don't have to watch the whole thing. Hopefully you can jump around and find out, and it's not too far into the video where we talk about fields, the definition of those, and some examples. We talked about the set of real numbers being a field, the set of complex numbers, the set of rational numbers, the set of integers is or is not a field. It's not a field, is it? Because it doesn't quite satisfy all of those properties of a field. We do not have a multiplicative inverse with the set of integers. Those do not form a field of numbers, or just a field. One vector space, a very simple vector space, is the real line. We could have that as our vector space. But in general, what we want to do is sort of think of this vector space in a more general context and say it's really a collection that we can linearly combine with, not just always columns of numbers. When we think of vector, a lot of times we just immediately focus on this column of numbers, but a vector doesn't necessarily have to be a column. It could be a matrix. That could be our vector, and we could be working in a vector space of matrices, and we'll maybe use that example in a minute. However, with the disclaimer here in blue, sometimes it is helpful to think of a vector, a tall, thin column that's representative of a vector space. So you just need to kind of keep an open mind as to what we're using or what we're doing when we have a vector space. I promise I'll quit scrolling in a minute. But this is one way to capture a fair amount of material. But you'll have access to this if you don't get everything written down now. But I think there is some learning advantage to you taking notes during class. And I'll slow down in a minute and start taking notes with you, or writing down, and then you can maybe write down some, and you know you can fill it in later if you want to. I'll post those captured notes. As one entity that we may use throughout this semester is this set of all polynomials. And in this case, it's showing that we haven't yet made that finite, or we haven't terminated it. We could just say the collection of all polynomials, P of f. That means that we could have a polynomial that is of any order if we wanted to. And we might just denote that as script P of f. And what's f? It's a field, and it could be generally in the textbook, when they say f, it could be either the reals or the complex numbers. So f could be either of those, meaning our coefficients, a sub 0, a sub 1, those could be complex coefficients, or they could be real, and z, which is our variable in the polynomial, that could be either coming from the set of real numbers or the set of complex numbers. What if we looked at the set of second-order polynomials over the reals? Then we might write that with this notation. We might include a subscript 2, and now we might explicitly say, instead of f, we might explicitly say, oh, that's the real numbers. Our coefficients, somebody wrote on the screen, maybe you can't see that, but I can. I don't have a pen, luckily, to write on the screen. And you won't be able to see that if you're watching this online. You won't see the extra markings on the projecting screen here in the classroom. But the a sub 0, a1, a2, That's as far as we go. We said it's a second order polynomial. Those can be real. Those are real numbers. And x, the variable, the independent variable in this polynomial, that's also belonging to the set of real numbers. And we can then define this vector space of a collection of second order polynomials in this way over the reals. Now you could also think of that vector space, script p sub 2 of r, like R3. Meaning you could say, oh, if I now have a polynomial as a function of x, p of x is now a sub 0 plus a1x plus a sub 2x squared. We could relate that, or we could say that is the same or corresponds to, that's what I'm implying by this arrow. Oh, and I can't move over it very fast. A sub 0, a sub 1, a sub 2. And we could then categorize we could think in terms of R3, or we could think in terms of a polynomial. Both of those are capturing this vector space of second order polynomials. That's one example of a vector space that we didn't talk about before in yesterday's lecture. We can also think of the vector space of, let's say, 2 by 2 matrices. So that now M is some 2 by 2 matrix first row, let's say AB, second row is CD, such that A, B, C, and D, let's say in this vector space, belong to the set of real numbers. That vector space corresponds to or is the same as what, let's say, real vector? What real vector would this this 2 by 2 matrix correspond to? Pardon? Okay, it could be A, B, C, D, right? It could simply be now some R4. It could be a 4-dimensional vector where the elements of that 4-dimensional vector are consistent with A, B, C, D in your matrix. So whatever you could sort of demonstrate with the 2 by 2 matrix, you should be able to show that the similar type of analysis or thinking could be made from R4. So if you're not able to sort of see what's going on with this 2 by 2 matrix, you could say, well, let me look at it as far as a R4, or a 4-dimensional vector of real elements. And now let me get a handle on what's going on. Then you restrict A, B, C, D in your 4-dimensional real vector to be consistent with the location in the 2 by 2 matrix. What are some other, yes? So now the question was, does it have to be a R4 or a 4-dimensional vector? It could be some other 4-dimensional entity. Maybe it could be a, well, it could be a row vector, or it could be, I having a hard time thinking of anything other than a square matrix that it would be, or a 2-dimensional, or you could, but it has to have 4 objects or 4 elements. But typically what is going to happen is you may have this vector space and you want to know how many independent variables do I have, then you may be associating it with r to the whatever that independent variable number was. And now you're thinking about it like it's a vector. Like I said, maybe you don't want to always be thinking that way. But here, if you are comfortable with that, now you can translate it to that representation and maybe get more comfortable with what you're talking about or dealing with. Another vector space that maybe is not as obvious is the following. A vector space F, which is some function such that we map the natural numbers into the reals. And we need to show that indeed this does satisfy the properties of a vector space. Let's just look at some examples of functions that might belong to this vector space. For example, we might say a particular function, let's say f sub 1 of n is actually n plus 1. That takes an argument of a natural number n and produces a real number, n plus 1. Another function, f sub 2 of n, is, let's say, 2n squared minus n. Not that we're validating this as a vector space, but we could see if these two functions belong to the same vector space. Is it closed under addition? Meaning we could say f of n, let's say that's f sub 1 of n plus f sub 2 of n, or the sum of those first two examples. That now says that we're adding n plus 1 to 2n squared minus n, or we now have 2n squared plus 1. Does that belong to the vector space as we defined it? This now is its domain is the set of natural numbers, n, and it does get mapped into the set of reals. So that 2, this also, this f of n, does belong to that vector space. And those two functions then are remaining, their algebraic, their sum belongs to the vector space. And you could then think of, well, what does that correspond to? Well, then you would need to sort of look at what does this f of n look like as a maybe something that looks more like a vector. Now you might say, oh, I need to evaluate this at all of my natural numbers. And then that is no longer finite dimensional, is it? But if we looked at some of these, at n equals 0, it's 1. At n equal 1, it's 3. At n equal 2, it's 9. At n equal 3, n equal 4. N equal 5. You guys are good at this. Have to go back and show me what that is. 25 times 2, or 50 plus 1, is 51, right? And you could just keep going. That then corresponds to, now I have to remember what it was, 1, 3, 9, 19, 33, 51, and that doesn't end, does it? That's an infinite dimensional vector, which we may not be using in linear. algebra done right. There will restrict to finite dimensions, but this is still a vector space. So this is now an infinitely tall or an infinite sequence. Again, a vector space. We can also have vector spaces that are functions. We could say V, a vector space, is the set of functions that takes as its argument some element of the reals and maps those into the set of reals. Meaning that could be one vector in that vector space, right? That's just one of an infinite number of vectors that belong to that vector space, which is the set of functions f, such that you give me a real number, x, and it will map to another real number. That's a vector space. So now we could have a vector space of functions. So we're trying to sort of generalize this idea of just tall, thin, skinny vectors. F now is a vector in our vector space. And you could have g of x, for example. That also is belonging to that vector space. You could have an f sub 2, an f sub 6, all just functions of this real variable x producing or having a range of the real numbers. One more vector space. We could restrict or that's pretty rich, isn't it, in terms of the functions that satisfy or belong to that vector space. We could say, well, let's look at something a little less full. Let's say that we're interested in functions f such that real numbers get mapped into real numbers, but, or this, that's not a but, that's a such that. So that vertical line means such that these f's, these functions, let's say, satisfy this differential relationship between f and its argument or domain x. So now the second derivative of f with respect to x plus the function itself need to sum to 0. And that collection of f's is now making up this vector space. And that collection of f's you can show satisfies those properties of a vector space. Commutativity, associativity. It's closed under addition, closed under scalar multiplication. That still defines a vector space. What is a potential member of that vector space? Yes, it could be cosine of x, or we could even say, let's even make it more involved, let's say plus b sine of x. And if that's the case, then this particular f of x, we could say corresponds to AB or R2. So those are some examples of vector spaces that you might not have thought about when somebody says, oh, you're playing with vector spaces, you're just doing linear algebra. You're just looking at tall, thin things. We can generalize that. We can have our vectors be something else. Let's now look at some properties that these vector spaces satisfy. And these properties that I'm talking about right now are collected on pages 11 and 12 of Axler. Proposition 1.2. This says V, a vector space, has a unique additive identity. What does that mean? V has a unique additive identity. What's the additive identity? You add it to a vector and you get your original vector back. So this is like the zero vector, and that's unique in your vector space. You have a zero element, and it's unique. That's proposition 1.2. So if you have a vector space, you know it has a unique additive identity. 1.3 proposition. Every element in a vector space, or in V, has a unique additive inverse. And a lot of times it's helpful to just give yourself a concrete example to hang your thought or thinking on. If you simply think of the real line or the real numbers being a vector space, now in proposition 1.3, that simply says, you give me an element on the real number line, 6. What's its additive inverse? -6. And that's unique. You take another element, 2.7. Not quite E. 2.7. -2.7. So you can sort of quickly try to hone in on what in the world does that mean? Now you know, just by one or two examples from proposition 1.3. 1.4. Proposition. If we take 0, V is equal to 0 for every V or element in your vector space. V is a vector. Here's where it might, and I maybe did this intentionally, those zeros look the same, don't they, in my writing, but they're definitely not the same. That makes sense? The 0 on the left is what? That's a scalar, isn't it? If I'm scaling, if I'm multiplying it by a vector. The 0 on the right, that's our additive identity, isn't it? That's a 0 vector. So this 0 is a scalar. This 0 is a vector. Is that clear? Is that completely confusing? 0V equals 0. But now, what is 0? It represents something different on the left versus what it is on the right. Yes? What's flipped? V is a vector. V is, so now think of it as a tall, thin column, or just V is a real number. That's maybe not as useful because then the zeros are the same, aren't they, effectively? So now make V a tall, thin vector, but this could be V belonging to one of those other vector spaces. Maybe V is now a function, but it's also called a vector. So now you would have, let's say this is a function. This is now the zero function instead of just the zero scalar. Yes? So the question was, is it okay if we add zeros to our vectors? And what did I say? It's been a long day. Thank you for correcting me. So I think you're wanting to do a bold face or an arrow above the symbol, and I wanted to say no. Let's make it. No, it's okay to add a arrow above the symbol. I'm just wanting you to be aware of in the textbook that may not be the case. It may not be, it's supposed to be clear from the context, and that's sort of this level of mathematical maturity that they're wanting you to develop. So now we've grown up, so to speak, and we can see just from the context that the one on the right, I don't need that to have an arrow above it. That's zero. That's a zero vector. It depends on what that vector represents. It may be a 2 by 2 matrix on the right, and the element on the left is a scalar, and you wouldn't have put an arrow above that to begin with, right? So yes, please make sure that I'm saying what I want to be saying when I'm talking, because it's going to be very confusing to you and to the people listening to this. What in the world he's talking about? Zeros above a vector? No, an arrow above a vector. Thank you. Is that clear? So yes, you can, but maybe you want to get used to not having to necessarily do that. But I think as you're learning, that's fine. But I may not be doing that. I may just say, oh, that's clear from the context. And that's what happens a lot of times when you're reading something. But if you put it into concrete examples, it might be easier for you to think about what's actually each of these is represented. Let's do it a little bit different now. Proposition 1.5. Now let's say we have A0 is equal to 0 for every A in our field, F. Now, is my 0 on the left, what is it? It's a vector, isn't it? Because A is the scalar. Here, our zeros are the same, and they're on opposite sides of the equality. We have a 0 vector on the left, we have a 0 vector on the right. And it's clear from context. Is that okay? Meaning here, I could say vector there and there. So no matter what you pull out of your field of numbers, if you use that to scale the 0 vector, that's going to be made equal to the 0 vector. That's proposition 1.5, and that's true for every vector space. Proposition 1.6. The scalar minus 1 times the vector v, we will let that be minus v for every v in our vector space, capital V. And now it may be difficult as to what am I saying. V, that should have been clear that that was a lowercase v. No, it's not clear, but you have to try to understand what I'm saying. So little v, I should say lowercase v, is a vector. We scale it by -1, and in a vector sense, if you were thinking about a directed line segment from the origin to some point in, let's say, the plane, then you hit it with -1, you're now going in the opposite direction. Questions on those propositions? We just basically stated those. Oh, shouldn't have asked. Yes. So now yes, sometimes it depends on the terminology. Sometimes it might be that somebody says, oh, here's the set of propositions, and these are the foundational ones or the fundamental ones, and we'll use those to prove everything else. But in this, these are sort of provable statements, these propositions. So we're going to prove, let's say, proposition 1.3. We're not necessarily going to just say that that is a fact, a proposition, and we're going to just live with it. Some of these may not be that easy to sort of prove, and so we're just stating those as propositions. But, oh, yes. Yes, so the negative v is our notation for the additive inverse of v. Yes, so we are essentially saying -1 times a vector, we'll just represent that by -v. And that's why that one's a proposition, let's say. Now, if we did want to prove something, and we may not want to prove these propositions, but I will go and try to prove proposition 1.3 in a minute. But let's just talk about some proof techniques. How many in here have had a class that was very theorem proofy already? So this may be a review, but some of you maybe have not seen this before. So this is why I'm sort of going over this, but I'll really just go over it fairly quickly, and you may want to do some more on your own. So here, just to give you the overview, you can see the inside covers of the optional textbook by Solo. And in general, these proof techniques, let's say you want to prove some theorem, you're starting with a statement, you're doing some analysis or some logic, and that should then, let me just say a statement, not statements, a statement yields another statement. Or you could say we start with some hypothesis, and that yields a conclusion. Or we might just abbreviate that and say A implies B. Or if A, then B. Those are all statements, let's say those are all ways of representing a theorem. You could have a statement yields a statement. You could have a hypothesis. You can then lead you to a conclusion. You could say A implies B, or statement A, if statement A, then statement B. So if A is true, then B is true, is what that's meaning. Let's just quickly go over some techniques of verifying or validating those relationships. We might use a direct technique, and that's not necessarily always the easiest technique to use. That's why we have others. But here, in a direct technique, we might start with statement A, and progress to showing B is true. And that may not be easy to just immediately see that chain of operations or derivations to make it start with A and end with B. You may actually sort of want to start at both ends and work towards the middle and then put it all together from A to B. You may want to work from ends A, B. And you might hear this referred to in the optional book as this sort of forward-backward proof technique. That's one. That's the direct approach to proving a theorem. Proof by contradiction. In this case, you can start with A and the negative of the conclusion. You start with A and not B. And with those two, you try to derive a contradiction or a false statement. Square root of 2 is equal to 1, for example. That's a false statement, I hope. And that would then say, oh, proof by contradiction. Started with A being true, started with the conclusion being false, and you derived a contradiction. Those two couldn't happen together. You couldn't go from A and show not B, basically. Direct contradiction, then we have contrapositive. Proof by contrapositive, which means you start with not B and show what? Not A. If you can start with the negative of your conclusion and show that that implies the negative of your hypothesis, then you've shown that if A, then B. And that you can sort of look at a truth table and show that if you start with not B, the only way that that truth table is going to be true is if you have not A. So in this case, you assume not B and progress to show not A. Depending on what you're working with, sometimes a proof by induction is nice to use. In this case, you simply prove the base case, which might be the case when n is equal to 0 or n is equal to 1 or n is equal to 2. It depends on where you've started. Then you assume this relationship is true for n, where n is a generic n, and this is the referred to as the induction hypothesis. So you assume that it's true for n, and then you show that this relationship is true for n plus 1, where you're relying on the fact that it's true for n, using true for n. That's your induction proof. You prove it for the base case, and a lot of times that's almost trivial. Then you assume it's true for n, and then you have to show that it's now true for n plus 1. And that's now proof by induction. Let's demonstrate one of these. You may demonstrate more on homeworks, but let's just go over one of these. Let's say we want to proof of proposition 1.3. Using contradiction. Let's just remind ourselves of what we had for proposition 1.3. 1.3 said that every element in our vector space, every element in V, has a unique additive identity, or I'm sorry, additive inverse. Proposition 1.2 said that the additive identity was unique, right? So proposition 1.3 says you give me an element, any element, for every element in V, that element has a unique additive inverse. Proof. And we're going to use contradiction. What does that mean? Well, let's suppose V is a vector space. And let's just pick a generic element, little v, out of that vector space. Let's let little v belong to the vector space V. Now, proof by contradiction says assume not B. So now we need to basically assume that we have some non-unique additive inverses for V. So let's just assume that we have two different additive inverses. By way of contradiction, suppose, let's say W and W prime are both additive inverses of V. What we're assuming then that W and W prime are different. That's why we have a W and we have a W prime. Those aren't the same, but they're both additive inverses of V. That's what we're implying by saying, suppose we have a W and a W prime, and they're both additive inverses of V. Well, we're assuming now that W and W prime are different. Or that means they're not B, where B is we have a unique additive inverse. Let's now look at W. W is W plus 0. What's 0? Scalar or vector? It's a vector, isn't it? Well, we also know that W prime is supposed to be an additive inverse of V. So we could write that 0 as V plus W prime. So that we now have W plus V plus W prime. Where V plus W prime, by definition of W prime was an additive inverse of V. So that in parentheses is the 0 vector. But now we have this associative property, right? It doesn't matter how we associate the addition of these vectors. Let me add W plus V. and then add to that W prime. But what's W plus V by definition of W? The zero vector. But that's now W prime. And now we've concluded, therefore, W is equal to W prime. They're not unique. Yes, they're not different. W, if you give me W, that's the same as W prime if it's an additive inverse. So this is a contradiction of what we assumed. We assumed they were different, and now we've just shown they're equal. A contradiction since we assumed, W and W prime were different. Therefore, the additive inverse of any element V in our vector space is unique. And that's a proof of proposition 1.3. So now we have vector spaces. Can we look at sort of pieces of those vector spaces, or can we talk about subspaces? Not a subset, but a subspace of a vector space. And now we have to learn how to essentially distinguish between a subspace and a subset. So here is our subspace discussion. And it always kind of helps to have a picture. Here's a really complicated picture that I hope you'll be able to draw. There's our vector space, V. There's our subspace U. And that looks like a set with a subset. So we now need to make sure that U is more than just a subset. It has to now have the properties of a vector space to be a subspace. Suppose U is a subset of V if U is also, in addition to being a subset of V, it is also a vector space, then U is a subspace of the original vector space V. And what I was trying to make clear before is that there is a difference between a subspace, again, make sure I'm awake when I'm writing this down. There's a difference between a subset and a subspace. Or another way of thinking of that is every subset is not necessarily a subspace. Now, the nice thing about showing that a subset is a subspace is we don't have to verify every one of the properties of the vector space. That the U doesn't have, we don't have to demonstrate or verify that U satisfies every property of a vector space. Because it's a subset of V, it inherits a lot of these properties. So what we do have to do are three things to show that U is a subspace of V. In order to determine if U, which right now is simply a subset of V, in order to determine if U is a subspace of V, we only need to check three properties. And this is talked about on page 13 of the book. One of those three properties is that U has to have an additive identity. What's that mean? It has to have a zero vector, doesn't it? So 0 needs to belong or be an element of U. So if you can't find the zero vector in your U, if it doesn't belong, then U is not a subspace. That's one of the properties, because you only have to find one what do I want to say? Something that doesn't satisfy any of these properties, just one instance, a counterexample, and you've then shown that it's not a part or is going to be, will not be a subspace. The other property, the second of the three, is that we need U, script capital U, not YOU. You don't need to be closed under addition. Maybe you would feel better if you were, but the subset script U, capital U, is closed under addition. Which means if you take two elements, little u and little v, two vectors of U, and those are any vectors in your subset U, you need to be able to show that their sum, their vector sum, belongs to capital U, the subset U. Not only does capital U, this subset, have to be closed under addition, it also needs to be closed under scalar multiplication. Which means, depending on what your field of numbers are, F, real numbers or complex numbers generally for this class, and you take any element in the subspace capital U, then for any number in the field, scaling U, that better belong to the subset U, script U. All of the other properties of a vector space are inherited by U being a subset of V. The other vector space properties are automatically satisfied since U is a, whoops, not as an element, but is a subset of V. That's what that open symbol means. It's a subset of the vector space V. Let's look at some examples. Suppose our vector space is R2. Or that's your desktop. That's the Euclidean plane. That's X and Y, let's say. Suppose V is R2, or you could say V is the set of ordered pairs, X comma Y, such that both of those coordinates in the ordered pair, X and Y, come from the set of real numbers. That's our plane. That's the Euclidean plane. That's our overall vector space. Let's see if we can identify some pieces, subsets of that, that might actually be vector spaces themselves. 1. Suppose U is the set X comma 0 such that X is R. Whoops. We're still going. I was hoping that we didn't have a Wednesday class because I think the Monday class goes for 3 hours. So maybe they have a Wednesday different class that goes for 3 hours. We go until 5:15, don't we? I know you probably don't want to, but we do. Thank you for being honest. You didn't have to contradict that statement. What is U? Not U, Y-O-U, but capital U. Is U a subspace? Is U a subspace of the two-dimensional plane? And it may be obvious, or it may seem obvious, but let's just show it for this case. I think it's clear that it's definitely a subset of V, right? So U is coming from V. It is definitely a subset of V. Now what do we need? We need to show it satisfies 3 properties. The first one is that it has the additive identity. So now we need to see, is it possible for 0, 0 to be an element of U? If capital U is X comma 0, the ordered pair X comma 0, and X is the set of reals, does 0, 0 belong to U? Yes, we can just let X be 0. So this is let X equal 0 in the definition of U. Is capital U, this subset, closed under addition? So now pick an arbitrary U1. Let's say that's X1, 0. An arbitrary U2, let's say that's X2, 0. Does U1 plus U2 belong to capital U? And it does, doesn't it? Because this is now x1 plus x2 comma 0, well, maybe I'll be very explicit, 0 plus 0, which is x1 plus x sub 2 comma 0, and that is in U by definition of capital U. What about, is it closed under scalar multiplication? Let A be a real number. And U1, let's say, be x1 comma 0, which is in U. Then AU1, which is A times x1 comma 0, is AX1 A times 0. Well, I'm going to have to go out and scold him, aren't I? In the hallway. Is that in capital U? Yes. So U satisfies those three properties, which says that we can now conclude that capital U is not only a subset of V, but it is also a subspace of V. We could say U is a non-empty subset of V that is closed under addition, closed under scalar multiplication, and contains the additive identity. Or zero vector. What about another one? Let's say W is the set of ordered pairs 0y. Is W a subspace of V? And we won't go through that. That would be exactly the same proof that we did, or verification of those three properties from before. What about M equaling the ordered pair x1, x1, such that x1 is some real number? Is M a subspace of V? Is capital M? Yes. You were just drawing a line. Yes. So you're animating M, capital M, right? Capital M is, let's say, this 45-degree line. And that's fine. That's what we need to do. We need to get active when we're learning. So now you can just sort of do that, right? And pretend you're flying. Now we have x1 comma x1, and is that a subspace? Yes. It satisfies the additive identity. Meaning we can pick the ordered pair 0, 0 with x1 equal to 0. We have x plus y equaling x1, x1 plus y1, y1. That keeps us on the 45-degree line. This is now x1 plus y1, comma x1 plus y1, which is an element of M. And finally, A being some real number from our field of real numbers, and U being, let's say, x1, x1, then AU is AX1, AX1, and that's the same, or I'm sorry, that belongs to M. M is a subspace of V. Let's look at some other set. Suppose we have N, which is x comma y, such that x and y are integers. So x is an integer, y is an integer. That's a subset of V. Is in a subspace. So now you could sort of think of this grid, Euclidean plane, and now you have dots on these integer points on your grid. I have a grid here, and now you could just think, I have all of these points. Is that a subspace of V, of the Euclidean plane? Is everybody okay with this being a subset of V, which is R2? So we have to do more than say, oh, it's not even a subset. It is a subset, isn't it? And does it satisfy property A? The origin is in N, isn't it? So that one's okay. We can let x and y both be 0. What about U equaling U1, U2, and V, I don't know why I'm changing my strategy, being V1, V2, U plus V, U1 plus V1, U2 plus V2, that's in N also, isn't it? So maybe we should have started at the other end to find a counterexample. And that's, I think, what you were doing. However, the third property, let's let A be in the field of real numbers. Now U, let's say U1 comma U2 is still in N. But now I just have to find one little a to show that A times U is not in capital N. One counterexample could be, suppose A is 1/2 and U is, let's say, 1 comma minus 2. Then we can say that that implies that AU is now 1/2 times 1 minus 2. That's now 1/2 minus 1. The second coordinate looks okay. The first coordinate's not. That's not in N, so therefore N is not a subspace of R2. And we'll pick up with vector space sums and direct sums maybe on Labor Day. You don't have to be here on Monday. I'll do that and you can watch it. Okay, so hopefully that will happen. And look for homework assignment number